All right, so we've been dealing with the equations of motion directly up until now. Well, Newton's second law, force equals mass times acceleration. Now we're going to work. We're going to work, or we're going to discuss another topic, which um, is often a more convenient way of solving the types of problems that we're going to be addressing in this course. All right, and that's the concept of work and energy and the relationship between work and energy and things like that. So first thing we're going to do is define work in the physics sense. All right, and so as an example, say we have you and a friend or something. You have a car that's broken down, right? Broken down. Your buddy ran his car out of gas or something like that, and so he calls you up, and you got to go help him push his car over here to the gas station. So the path of the road is known, right? So you're going to be pushing the car along the path. You decide to push the car in such a way that it's tangential to the path. So you get behind the car and you start pushing. All right. Your buddy, not being all that bright, decides to push perpendicular to the road. All right. So just from an intuitive sense, only one of you is doing any good. Okay. The person who's you in this case, pushing in the direction tangential to the path, you're the one that's actually making progress. Okay. The resultant force, of course, is going to be the sum of the two forces being applied to the car. So the question is, how do we determine, given an arbitrary force, how can we determine how much of it is doing any good? Which, of course, from our standpoint, doing any good just means increasing the speed of the vehicle. All right. So, the resultant force is equal to the sum of the tangent component times the unit tangent vector plus the normal component times the unit normal vector, right? Kind of by definition. It's also, just for completeness sake, there's a binormal component, but this will always be zero. And we discussed this before because of the fact that the acceleration in the binormal direction is always zero. And since force equals mass times acceleration, the force must also equal zero, the sum of the forces. Now, the binormal force in this particular situation would be, gravity and the resistance of the Earth to the gravity. You know what I mean? The surface of the Earth. So it doesn't matter. These things equal zero. The sum of the gravity and the equal and opposite force provided by the ground must sum to zero because there is no acceleration into or out of the page here. All right. So because the tangent and normal, it's a consequence in every situation that we're going to be dealing with and that we have dealt with so far. The component vectors, or the basis vectors, are perpendicular to one another. They're what's called and they happen to be of unit length, so they're called orthonormal basis vectors. All right, that's not really important to us. We're just going to be dealing with the consequences there, but if you're interested, you can come ask me, and I can show you some examples where some of the math that I'm about to show you now breaks down in the event that these things are neither orthogonal nor of unit length. But because they are a unit length and because they are perpendicular, I can write this equation. Okay, so the tangential component is just the dot product of the force with the unit tangent vector. And remember, the unit tangent vector is tangent to the curve by definition. All right, and then so this was another definition of the unit tangent vector. And if you remember, so the velocity is that, and the speed is also given by this so the speed is also equal to the change in arc length over unit time, as well as the velocity vector is just the first derivative of the position vector, and the differential times cancel, so dr ds is the unit tangent vector. And this is kind of a review, maybe a restatement of what we learned before. Now, if you remember, another thing we learned previously is that the tangential acceleration is equal to the change in speed with respect to time. And the speed is the change in position along the path, or ds, with respect to time. And then so dt, I can solve both of these for dt, and so that is dv over the tangential acceleration, and it's also equal to the like a differential change in position along the path divided by the velocity. And as a consequence, this is a convenient. This is remember this relationship, we've already actually discussed it in previous lectures, but it's just a fundamental fact that we can take the the acceleration times the differential change in position, and that's going to be equal to the speed times the differential change in speed. And I can multiply the mass times this. If I multiply through by the mass of the particle in this case, I get this arrangement. Well, what is this? That's just the tangential force. Okay? So what we have here is the tangential force times the differential displacement there is equal to the mass times the velocity times the differential change in velocity. Okay? Now, like we've discussed up here, the tangential component of force is just the force times the unit tangent vector. And so now so we can use this fact so that and the sort of the ds's cancel there. So So this is kind of a more general way of saying the exact same thing. So if I have the force and I dot it with the change in position, and the change of position, realize it's always going to be in the tangential direction, right? By definition. So I have a small change in position, and that's going to be equal to this mv dv. All right. So what is this? First of all, this we can integrate this expression here. So if we integrate it from, say, R1 to R2, that's going to be equal, and then we integrate this side with respect to V. Well, this is just where T is called the kinetic energy. So the kinetic energy of a particle is just equal to 1/2 times the mass times the velocity of that particle squared. So this ought to be a review for you. Okay, but the consequence of this relationship here is that this quantity is called the work. The book gives it the symbol U, and so this will be the work from point 1 to point 2 is equal to the integral from position 1 to position 2 of the force times dr, where dr is taking along the path. So dr is a differential length along the path. All right, so you need a path to integrate that over. Or you can express this in differential form. And so as a consequence between these two things, the work done from position 1 to position 2, or from point 1 to point 2, is equal to the change in kinetic energy. Okay. So work is kind of if you do work on an object, you are lending energy to it, and work is only done in the direction of the motion. So your buddy here is not doing any work. He can push as hard as he'd like, but as long as he remains pushing perpendicular to the car, he does absolutely no work. You're the only one doing work. The resultant force is this. However, your buddy's portion of it isn't doing any work. Okay? And the force that you apply is accelerating the car, and therefore increasing the speed and having the effect of increasing the kinetic energy of the car via this relationship. So the speed that you give it is an increase to the kinetic energy according to that formula. All right, so that's pretty straightforward. The work is equal to a change in kinetic energy. And we're just going to reiterate this. Change in kinetic energy. Kinetic energy is defined in this way relative to a particle with velocity v and mass m. And then force is only done in the tangential direction of motion. Any force acting normal to the motion does no work. All right. So power. Power is just work per unit time. And the book uses a symbol P. All right. And so since work, or the power or work per unit time that you apply to this particle in this case is equal to the force that you're generating, dotted with the velocity of the vehicle. All right, so this is the definition of power in this case. And then there's a concept of efficiency that I want to define here. You guys, it's usually given the symbol epsilon typically. It's a unitless quantity. That's a good point. I want to come back to that for a second. I want to talk about units, but this is equal to, like, it's in general, efficiency is a desired quantity over the cost. And in this case, the desired quantity would be the kinetic energy of the vehicle, or the book says, like, the energy output over divided by the energy input, or likewise power out over the amount of power you had to put in. Now, units. The units of kinetic energy are joules in the SI units, in the SI system. Likewise, you can tell just from this expression that the work must also have units of joules, and then the units of efficiency are unity, or 1. It's unitless. Okay.